The next talk is Thierry Passot, who's going to give us, I guess, a more theoretical talk about Alfvén-wave turbulence as well. So highly related to what was happening earlier on.
I would like to thank the organizer for the invitation and acknowledge my collaborators. Some of them are actually not listed here, but that's the main person I've been working with recently on the last topic I'm going to talk about today. So the outline of my talk is the following. I will very briefly present motivations for the work taken from observations of the solar winds. I mean, we had such wonderful talks before that is my task on that subject. And then a few results on whole MHD, compressible whole MHD, just to introduce some topics. And then focus on the role of temperature and anisotropy, and introduce the tool I'm going to use to study that kind of problems, which is the Landau-Fluid model. And after some introduction about this model and its validation, I will present some simulations showing some features of development of an anisotropy and boundedness by instabilities. So as I said, I will be very quick on that kind of things. All of you know that we have a wonderful plasma laboratory around us, and that we have cascades, turbulent cascades that actually extend beyond the ion-Larmor radius. But not only that, we have a lot of observations of small-scale coherent structures from filament shocklets, solitons, magnetic holes, which are typical scales are the order of a few Larmor radius, and so it's quite interesting to actually focus on that scale, on these scales, the ion-Larmor radius scales, where dispersive and kinetic effects play a major role and are at the source of these typical structures, which actually can influence a lot the transport property in the turbulence. So you've seen these figures before. I would like just to draw your attention on the fact that this spectrum here, presented by Fouad Sahraoui in this 2009 PRL, has been actually obtained, as we said, as a frequency spectrum. But recently he performed also in a range of scale around 0.1 to this is the magnetic spectrum, magnetic energy spectrum.
Energy.
Yes. And the interesting feature is that using the capabilities of the cluster experiment in a certain range of frequencies, it was possible to actually do some K-filtering analysis to actually look at the properties of the waves that propagate there using a way of actually measuring the real wave number spectrum and not only temporal frequency. And what was obtained is that in that range close to the knee between the turbulent cascade and the MHD cascade and the sub-ion-Larmor radius scales, this technique allowed him to actually find that there are kinetic Alfvén waves and that the angle that of propagation with respect to the magnetic field was about 86 degrees. So even at that scale already, the anisotropy is extremely high. And so the question, I mean, the facts that we have is that there is excess of magnetic energy in transverse components. And the question about anisotropy, does it persist at small scales, is partially answered here, but the question is what happens when you go down to smaller scales. And there, of course, we lack some data to actually confirm what happens. And which kind of cascades, which kind of waves, which kind of slopes, which are important to actually estimate the heating. And finally, at what scale does the cascade terminate and actually dissipate energy? So one of the simplest beyond MHD model that can start to address this kind of questions is whole MHD, where whole MHD is only correct for very restricted parameter ranges like TI much smaller than TE, the small frequency ranges, and frequencies between the K parallel V ion thermal and K parallel V electron thermal velocities. So it only reproduces Whistler's and kinetic Alfvén waves for small to moderate values of the beta parameters, but do not contain the damping associated with Landau effect, and that actually can completely damp slow waves and thus change the nonlinear couplings. But nevertheless, there is a lot of efforts around solving these equations. There are some attempts in 3D here showing that indeed you get a steepening around the ion-Larmor radius scale to a K-7 possibly spectrum. This is still too low resolution to actually be sure of that. What I would like to show briefly is some simulations where we actually drive randomly with a white noise in time the transverse component of the velocity or magnetic field in one dimension, and show by varying parameters the influence of the dispersion strength, the influence of the angle of propagation, and the influence of the type of driving, and the spectral transfer versus coupling between various MHD modes. So what I mean by the influence of driving, I mean that if we want to mimic the turbulence at these scales, we need to actually mimic the down end MHD cascades and start with fluctuations that originate from this MHD cascade and go down to smaller scales. So we need to put some driving at these scales, and there is a lot of freedom of how to do that, and it's not clear which way is better to actually do that. What I will show is that there are some differences, but overall, I mean, the global results are not too dependent on that. So there were mentions this morning that a lot of pressure balance structures are found. And indeed, what happened, the most striking feature for the parallel propagation with the kinetic driving in a simulation domain, which is 16 pi times the ion inertial length for beta equal 2, is that the energy actually does not saturate. You keep driving your system, and the energy piles up in these local pressure balance structures. And if you look at the deviation between velocity and magnetic field energy, you find that indeed the kinetic energy dominates in these situations. I will show the spectrum later on. And you find that after you filter these large-scale modes, you find that the fluctuations of velocity actually undergo a very strong localized perturbation that behave exactly like solitary waves, even though they are not solitons, but we find some evidence of that. The spectra are non-universal at all. I mean, what happens is that you really indeed find a break in the spectrum at the DI scale, but this has nothing to do with different types of cascades here, because we are one-dimensional. This has to do with structures. I mean, the flow has different kinds of wave packets or different kind of fluctuations, and doing a Fourier transform of this typical spectra always lead, I will show you later on other simulations, always lead to this kind of break, which actually is a signature of small-scale coherent structures. And in this situation, we have done some frequency analysis and shown that you are dominated by ion synchrotron turbulence with a velocity energy which is larger than the magnetic one. So how does the dissipation actually occur? What we find is that in this situation, the energy preferentially goes to acoustic modes and is dissipated in the acoustic modes, and there is very little energy dissipated in the magnetic mode in this situation. So there is mostly, I mean, even if you drive Alfvén waves, mostly what you get is sonic wave turbulence. So in this, this is not too surprising. And actually, this is just a graph that shows you that the rate of energy transfer from Alfvén to magnetosonic wave, which is this very wiggly graph here, compared to the instantaneous parallel dissipation, which is the black line here, when averaged over 1000 ion-0 periods, give you almost a perfect match between the two, between each other. So this indicates that indeed most of the energy that goes into the Alfvén waves transfers to sonic waves and then dissipate. And this is confirmed if you take the same simulation, but instead of forcing at each time step, you just impose that the forcing is only applied when to maintain a total constant energy. And in this case, what happens is that the energy of the magnetic spectrum leaves completely this range of scales and is transferred to sonic waves. The small scales are not actually affected by this, but this indicates that in this range of scale, from the large to the ion inertial lengths, there is no transfer of magnetic energy. But if you do the same thing by taking a simulation domain, instead of 16 pi, you take 4 pi, so meaning much smaller scales, then this phenomenon does not occur. And what you get is that you get a full spectrum here, and that indeed indicates that there is a cascade of Alfvén wave in the parallel direction, as long as you have enough dispersion. And this is consistent with a weak turbulence analysis based on the Vlasov equation performed by Yoon and Fang in 2008 that actually shows that there can be some coupling between Alfvén waves and ion acoustic waves, and that in the end the energy can actually cascade in the parallel direction. But from the large scales they cannot. But starting from the dispersive scale, indeed, if the forcing is there, you can drive a cascade in this direction. In oblique directions, you still get the pressure balance structures, which are this time perturbed by dispersive shocks and Whistler waves. And in this situation, the spectra is dominated by the magnetic energy instead of being dominated by kinetic energy. And at these scales, if you perform a frequency analysis, you really show that the Whistler waves are dominant in this situation. But if you, again, force your system at smaller scales, then the kinetic Alfvén waves, or the associated branch to it, seems to have a significant amount of energy. So this was a very simple introduction to the field of dispersive Alfvén wave turbulence. What I want to show now is the role of temperature and isotropies, and this cannot be addressed, of course, with whole MHD. And in order to motivate that work, I will show some plots obtained by Sarawi in 2006, showing that in the magnetosheet, where there is a significant role temperature and isotropy, you can actually not only observe mirror modes, but you also observe a kind of so-called mirror turbulence. And this has been actually shown by doing also a K filtering analysis in this magnetosheet fluctuation, and shown that actually the power spectrum of magnetic field intensity obeys a power law. Actually, the power, interestingly, this is the first real power law observed in K space and not in omega space, because in omega space, the frequency spectrum is close to -7/3, and the real K spectrum is close to -8/3. In this magnetosheet region, the approximation of Doppler shift is absolutely not valid, because all velocities are the same order, and you really absolutely need to go to a more sophisticated analysis. So interestingly, then you find that in the regions where all these modes seem to obey this power law, they are identified as mirror modes, and they are damped. So obviously there is a signature of nonlinearity here, and of a certain kind of cascade. And if you look at the distribution of energy along different directions, you really see that it's very anisotropic, and it's linked to the fact that the magnetosheet is actually not a very big system. You are bounded by the magnetopoles. You are also influenced a lot by the flow along the magnetosheet. And actually what happens is that the turbulence develops preferentially along the velocity, the main velocity component. And in the other directions, it's rather not clear and developed turbulence. So motivated by this,
sorry,
yes.
I probably missed this, it faded out. In laboratory plasmas, we have something called magnetosheaths that might be different than what you're talking about. What do you mean by magnetosheath here?
A magnetosheath, I will go back to. Magnetosheath is the region between the magnetopoles here, which actually is the transition between the the terrestrial magnetic field and the solar magnetic field, and the shock here. So this is a region bounded by these two lines, two surfaces. And that's a region where you undergo, after the shock, heating in the perpendicular direction for the ions, and then in this situation generate either Alfvén ion cyclotron instabilities or mirror instabilities. And there is of course a flow along this region that actually generate a lot of anisotropy in the turbulence. And once again, this famous plot that was presented this morning many times, and so I don't need really to go into the details. It's just to motivate the study I'm going to show you. And the motivation is again to actually understand a little bit the role of this mirror instability threshold here in preventing the fluctuations to actually go beyond that line, and understanding also the role of temperature and anisotropy on the spectrum at small scales. So the goal is also to understand the quantitative description of turbulent heating, characterization of the developing temperature and anisotropy, and analysis of the resulting mirror instabilities and their feedback on the turbulent dynamics. And finally, what kind of wave dominates in these regimes where you're really dominated by mirror instability. So how to address this question? Of course, I mean, we could run a 3D Vlasov-Maxwell simulation, but it's hardly possible, even though some attempts, I mean, some preliminary work is done in that direction, but it's still very hard. We could do gyrokinetic simulations, but in the presence of anisotropy, at least at the beginning of the simulation, would not really be for the moment feasible, and still to be validated in the context of high beta plasma. So what we need is a model that allows for strong temperature anisotropies, and that also does not a priori orders out the fast magnetosonic waves, as does the gyrokinetic assumptions. So we resorted to use Landau fluids. So Landau fluids were introduced by Gregor Hammett and Perkins in 1990 as a closure that retains phase mixing and Landau damping. And it was then implemented by Snyder, Hammett, and Dorland in 1997 for the large-scale MHD dynamics closed at the fourth order moment, and then extended to dispersive MHD later on, and more recently extended to account for the gyrokinetic scaling in the perpendicular, quasi-perpendicular directions to actually include the proper finite Larmor radius corrections that are necessary to actually treat properly the mirror instability, for example. So in this Landau fluid description, the fast waves are retained. They are only accurately described up to, but not beyond, the ion gyro scale, because this would require to actually use an expansion that does not assume omega over cyclotron frequency much smaller than 1, but this is the assumption we use. And also has to be mentioned that Landau fluids, like gyro fluids, do not take into account wave trapping, but in a turbulent context this might not be such a big problem.
There is some wave particle trapping.
in gyrofluids?
Yes. For example, if you have magnetic perturbations and P not equal to P parallel, that pressure anisotropy describes particle trapping through the CGL pressure tensor. But anyway, this is a subtle point, and the amount of accuracy of it, of course, up to it.
Yeah, the model is
It's
rather
not necessarily highly accurate in all regions.
Might be interesting to talk more about that. So just to show you the equations I'm solving, I briefly go to show you these are the proton fluid equations, which are an exact outcome of Vlasov-Maxwell. We assume quasi-neutrality. We do not take into account electron inertia, even though it's possible to actually do it. We have this Ohm's law taking into account the Hall effect and the electron pressure gradient terms. And we assume that the pressure tensor is just a gyrotropic form plus finite Lamoureux corrections. Then for each particle species, electron and ions, we solve the equations for the pressure, parallel and perpendicular pressures. We solve the equations for the heat fluxes, the gyrotropic heat fluxes components. And of course, as you see, this must be closed at some points. This equation for the heat fluxes, which are nonlinear, and this is a very important feature, by the way. If you take the same equations and linearize the heat flux equation, the results are quite different, actually. And so it's important to keep nonlinearities up to that level. And the fourth order moments, or their deviation to the Maxwellian value, have to be actually obtained from kinetic theory, and this will be the closure that I'm using. I'm also using non-gyrotropic contribution to the fourth rank cumulants. They are important to take into account, and they are also obtained from kinetic theory. So this
the fast magnetosonic wave is?
Excuse me?
You said you're keeping the fast magnetosonic wave. Is that
Yes, because
term?
the this equation, as you see, are not written in a drift expansion. They are written in the usual way for MHD, so they contain all the waves. And as I mentioned, the fast magnetosonic waves are not properly described up to Kepler-Rolle much larger than 1, because in order to do that, you would need to actually take an expansion of the linear Vlasov-Maxwell operator, keeping terms high order in omega over capital omega. And this we don't do because it's awful. So we decided to do that. So the fast waves are valid up to basically the ion Larmor radius, and then their dispersion relation might differ from the correct one. So the two main problems that remain to be solved is how to close these fourth order moments and how to calculate these finite Larmor radius corrections. And as I said, we base ourselves on linear kinetic theory in the low frequency limit. And the domain of validity of the expansion in Fourier space is the following. You have to have large scales in the parallel direction, as any fluid approximation would require, because then in this situation, gyrokinetics cannot allow to go to small scales. But in the perpendicular direction, we have a very good cone of validity up to scales which can go much beyond the ion Larmor radius. So just to give you a flavor of the kind of equations we get for the fourth order moments, what we do is obtain the fourth order moments from linear kinetic theory, replace the dispersion function of the plasma by a suitable Padé approximant, and after some little small calculations, you find an equation, linear equation for the fourth order moment perturbation, the cumulants, of this form, where actually the important term here is the Hz, which is the Hero transform in the z direction, so along the main magnetic field B0, and this actually is the manifestation of Landau damping. It's the manifestation of the absolute value of k in Fourier space that you obtain in Vlasov Maxwell expansions. And what we have to do, of course, is that these T0, which are the basic states around which we perturb, are replaced by instantaneous fields average, because in the simulation the temperature increase, and so we have to at each time step consider that all the coefficients are recalculated based on these local values. We do the same thing for gyroviscous tensor and other terms to actually combine the various fluid quantities obtained from linear kinetic theory to eliminate most of the occurrences of the plasma dispersion function, and for example end up with a simple formula like this, where the divergence of the pressure tensor, or the perpendicular divergence of the pressure tensor, is given by two functions a and b, where you see here the a depends on velocity and temperature with coefficients which are the usual Bessel functions coefficients that we can get. So this is quite simple, and as I said, we keep all nonlinearities of the fluid equations but linearize the kinetic effects. So to show you a few numerical tests, I will show you some results obtained both from the diffusion of a temperature gradient to show you the effect of this Landau damping, and on dispersion relation of mirror modes and kinetic Alfvén waves to show you the linear properties of the system. So on this thing, unfortunately, it doesn't show well. I should have kept the PowerPoint thing, but in order to show you what happens, on the diffusion of a temperature gradient, we take an equilibrium where this is the temperature and this is density, so pressure is constant, and you have a jump in temperature at the center of the domain. And we've done Vlasov simulation with André Mangenet and Francesco Califano, who is here, to actually show the evolution of the quantities, and we have done analogous Landau fluid simulations. What is important here to focus on is the fact that if you assume that the heat flux is a gradient of temperature, it should be the above curve, the dotted curve here, which is just this fluctuation here, which has nothing to do with the directly obtained profile from the Vlasov kinetic theory here. And the comparison between the two is, of course, you don't see the scales, but this is not on the same graph, but it is quite good for the two simulations. So this is as long as you don't have a scale which goes down to two short scales. Right? For example, the size of the domain here is 20,000 debye lengths, electron debye lengths. So if you take a smaller domain, then you will start having problems with electrostatic instabilities. But as long as you are in this regime, the heat flux is well reproduced. So for the linear stability properties, linear growth rate of mirror modes, here I show a few graphs of the kinetic theory in solid line, and the dotted lines here correspond to the result from the numerical simulation of the Landau fluid model. And you see here that for different parameters, except here when you are in a regime where you start adding some electron temperature anisotropy, which actually makes the mirror instability much harder and the growth rate higher, you will see that there is a small deviation here at the top. But otherwise, you have a very good approximation of the dispersion relation for mirror modes. In the same way, kinetic Alfvén waves are obtained for very large angle with respect to magnetic field close to 90 degrees, are correctly obtained up to scales which can be of let's say 50 or 20, well, K per pro of order 20 or 50. So this shows that this model has the same kind of ability to reproduce linear kinetic theory as the gyrokinetic model, but of course in the same way as the gyrokinetic equation have the same problem. For oblique propagation, you get very big deviations between the kinetic theory and this Landau-Fried model due to the fact that we do not capture resonances. And so in this situation, as long as if you fall outside the cone of validity of this system of equations, then you have to restrict yourself to scales up to the Eigen-Larmor radius, but not smaller. So I would like here to talk about some property of this Landau-Fried model, basically on the linearized system of the Landau-Fried equations, which might be of interest in respect to the plot that Stuart and Justin have shown this morning. What happens is that the linear system of equations is such that the matrix obtained by linearizing the equations is non-normal. So what does it mean? It means that actually the eigenvectors are non-orthogonal. And this, we know, can be very important in giving some transient effects in the linear system. And usually it is known that in fluid mechanics, when you have gradients, like in shear flows, you can have very strong amplification in the linear regime of initial perturbation that then go down to stabilize. Here, what we show is that this property is also true for the system of interest here, but also in a situation where you are homogeneous. You don't need gradients to actually drive this kind of transient instability. So, as I recall, in normal mode theory, the focus is on eigenmodes, which are assumed to grow or damp exponentially in time. Attention is only paid to asymptotic in time behavior. Here, we are going to look at transients. And if you here compare, for example, the outcome of modal theory, which is the dotted line here, to the solution of the linear problem, you see that you can have amplification of a factor of more than 100, or even here almost 10,000, for very long times. This is here T in cyclotron frequency, in cyclotron units. And you see that this amplification can actually persist, and this amplification is also more important at larger values of beta and also at smaller scales. So really the kinetic effects are important, and actually recent studies have shown that if you take, for example, the whole MHD system, you do not have such effects. You really need the presence of highly damped modes in order to drive these transient effects. And if you look at what happens now in a plot similar to the ones that were plotted this morning, except that it's for electrons here. So here is 1 minus T perp over T parallel of the electrons as a function of beta. You look for the average over 10,000 random initial perturbation for each case of the outcome of the total norm of the state vector, or here of the magnetic fluctuations, and shows that indeed the fluctuations are amplified more and more as the beta is larger. But as time goes on, the amplification is localized around the frontiers, which are plotted here, of the stability domain. So basically what I want to infer here, that in the stable region, the properties of the linear systems are such that you amplify the solution and can then probably scatter and reduce the anisotropy, even though you are not in the unstable regime. So this has to be, of course, further studied and studied also in the context of turbulent systems. But it is interesting to mention.
How come your magnetic fluctuations only appear to be along the upper threshold?
Yeah, that's the Firehouse threshold here.
That's the Firehouse.
Yes, yeah.
So you don't get the Whistler instability.
No, not in this thing, not in this situation.
Even though the state vector shows the Whistler.
Yes, the state vector, but this is for the delta By fluctuation, and in this situation we don't get significant fluctuation in this direction. So now, as far as nonlinear simulations are concerned, we are doing right now 3D simulation, but unfortunately, I'm sorry, I don't have results to present now on these three-dimensional simulations. Just to show you that the code exists and compares very well to hybrid peak simulations in the case of the propagation of an Alfvén wave in a density in homogeneity. For example, you have this formation of magnetic filaments. This is the result of Landau fluid. This is the result of a peak code. So we are confident that things compare quite well, and the project is to actually simulate now turbulence with this code. In order to actually progress in that domain, we have done 1D simulations. First of all, I would like to show you what can be obtained as far as the mirror instability is concerned, because this will be important for the interpretation of what we obtained in the turbulence regime. In the simulation of the mirror instability, the saturation of the instability obtained in the code leads to magnetic holes of the order of 6 Larmor radius in size for a situation of parallel beta of 5 and a temperature anisotropy of 1.5. And the plot actually compares quite well with cluster observations here shown in this paper. But the question arises of whether this mirror instability always leads to magnetic holes. It seems to lead to magnetic holes in this setup, in this fluid setup, but is it true in our setup? And actually, before going to that question, if you take the same kind of magnetic holes as previously shown here, and now restart the simulation and reduce the temperature and isotropy, you find that you can find stationary solutions even below the threshold of the instability. So it's actually a proof that the mirror instability is subcritical, and you can have solutions, nonlinear solutions in the form of magnetic holes below the threshold. Interestingly also, I will come back to that later on, but you'll find a large deviation of perpendicular velocity and magnetic field component in these holes, which are actually due to the Hall effect. And this will show that in turbulence simulation, this can be amplified by resonance effect to a very high degree.
Yeah, there's a result where if you look in the solar wind at the depth of these holes as a function of distance from the mirror instability threshold, the closer you get to the mirror instability, the deeper the holes tend to be. Mm-hmm. And we couldn't figure out if this was just some indicator of history or if there was some prediction theoretically that the closer you got, the deeper the holes might get. Do you have any comment on that?
Yeah, well, I mean, in the models we've constructed, indeed, if you go down further below the threshold, then the hole becomes weaker and then disappears. So there is a finite domain where you can have existence of that. Oh, sorry. So this is now to show you, I mean, are there always holes? Actually, no. I mean, the satellite observations first shows that the magnetic holes are mostly in subcritical regimes, basically in the regime below the threshold. This is the threshold of the instability. This is the skewness of the fluctuations, which actually measure. If it's negative, then it's mostly holes. If it's positive, it's mostly humps. So here you have mostly magnetic holes below and a little bit above the threshold of the instability. And these are, on the other hand, magnetic humps at large distance from threshold. This is obtained in the magnetosheet region. And indeed, you can see that from cluster and a paper by Suchek et al., you find that you can have both kinds of structures. So, okay, I mean, what happens now in the numerics? Now, we've performed in a paper with Francesco Califano and co-authors simulations with the Vlasov-Maxwell equations, and shown that in almost all simulations we've performed, this is a peak simulation in this case, we get only magnetic humps. We never get magnetic holes out of the mirror instability. And so the question is whether, what is the failure of this Landau fluid model to actually reproduce the formation of the humps? And we have a recent paper here that actually shows that in order to understand the transition, I mean the difference between formation of humps or holes, you have to really take into account what happens at the top of the distribution functions. And if you look carefully, you have a little bit of quasi-linear effects that flatten the distribution function. And this, if you take into account this factor in the nonlinear theory, can change actually from holes to humps or vice versa. And so,
But what is it's a definitional issue, right? Because
sorry?
is it not also just a definitional issue? If you have the holes are really, really large and all over the place, that's like having humps.
What is a hole in a hump? I'm lost.
Well, I mean, here you see clearly that, we do call that hole. This is clearly.
No, so you have the magnetic field and you get a drop out in it, right? So there's a drop in the field and that's a hole. Whereas if the field goes up and the density goes down, that's called the hump.
But the field
in the
drops between two humps and that's a hole.
No, because you normally, it's like the top right one, you get a relatively steady field with then objects in it. Yeah?
Yeah.
It's normally pretty clear to see where the objects are and where the background is.
So in the simulation, it's pretty clear that since you have this inverse cascade, actually, you get a coarsening and you really see isolated humps like this. And this is always what you get. So the question is, how do you get holes? Well, if you put holes at the beginning as a big perturbation in your Vlasov equation, this will lead to a stationary solution. Density, magnetic field drop, and this is stable. And if you put, on the other hand, a magnetic hump, it will not survive. So there is a difference in the stability of these systems. So the holes can be formed also after starting very far from onset. And so probably there is a selection mechanism. I mean, since the holes are stable and the humps are unstable, even though the magnetic mirror instability give rise to magnetic humps, they probably do not survive very long. And in the turbulent environment, we can expect to see a lot of holes, indeed, because these are the situations, these stable solutions of Vlasov-Maxwell equation. And indeed, in the solar wind, they find mostly holes, rather rarely humps. So that seems to solve the controversy. But yes.
Sorry, actually, if you go to the previous slide, you said from your simulation, you said that they seem to. You talk about coarsening. So
Yes.
is this the idea that you get lots of little ones?
Yeah.
And then
This is time here. This is spectrum, and this is time. So at the beginning, you get a lot of humps, and in the end, you get a smaller number, but much larger
and
amplitude.
the scale size of them has changed as well, has it? Is the spectrum changed?
The spectrum has moved to lower K, yes. You see, that's the K, and that's the amplitude of the magnetic field.
That seems quite a solid prediction. Is that something we see in the solar wind? I'm not offhand. Because I can't recall seeing things a lot like the left-hand side one, even upside down where there's holes on.
Yeah.
Whereas, and you do sometimes.
Oh yeah, you do sometimes observe isolated.
The right-hand side one is much more common. That's kind of what they look like.
Yeah.
They don't often look like on the left at all.
So, but that's a natural evolution of the system.
In the magnetosheath, you can see highly eroded regions where there's almost no flux, and it looks like it's because there were millions of holes that were created and emerged.
Yeah, I understand. There must have been that whole train of them. You saw that certainly in Jupiter's magnetic.
So now I will want to go to the main part, which is the simulation, the driven simulation of this Landau field model, choosing an angle of propagation of 80 degrees, white noise in time, either at k di equals 0.5 or 1, but applied on the perpendicular velocity component only if the kinetic energy falls below 0.05. So I just want to maintain a certain level of kinetic energy. The initial temperature is isotropic, and the parallel beta proton beta is 0.6. The size of the domain is again 8 pi or 16 pi in units of inertial length, so it's rather small scales. And the dissipation, I have to use some dissipation because at some point you will have very intermittent effects, events that I will show that actually force you to put some dissipation. But most of the time you actually don't need to do that because the Landau damping is enough. So here is the global evolution of the temperatures. So interestingly, what happens is that you find an increase of the perpendicular ion temperature, and the parallel temperature of the ions start to decrease a little bit and then increase, and then keep a certain ratio with the perpendicular temperature. As far as the electron temperature, this is the opposite. The parallel electron temperature is larger than the perpendicular electron temperature. So the turbulent driving hits the plasma and differentially with respect to ions and electrons.
I'm sorry, I was writing a note. You probably described this. How are you driving T from T parallel? Just random heating?
No, it's the only driving I'm adding in the system is velocity fluctuations in the form of Alfvén waves. So perpendicular to the plane kv0, I have a velocity uy. I drive it, and I maintain a certain kinetic energy in the system. And what happens is this kind of temperature grows. And
we should interpret this in terms of we've got some Alfvén waves propagating into the system, maybe from outside, and that's what's increasing the energy of the particles.
Yes, that's what I was saying. I need to mimic the end of the MHD cascade at some point. The MHD cascade injects energy, and then so I start from there. I cannot do the whole thing. So, and to show you
the electron flows would be quite different at that scale because of the FLR effects. So are you driving an ion flow or an electron flow or what?
Ion flow. I will show you that at some points there will be a very big difference between electron and ion flows. Yes.
Yeah.
Yes. So to show you the increase of the temperatures in the case of, for example, parametric decay of parallel propagating Alfvén waves, this is the opposite that happens. The parallel temperature increases, the perpendicular temperature decreases, and for the electron it's in the same direction, which is consistent with results of Mattei et al. So again, for the modulation instability, this is again different for the electrons. So the basic thing is that this is not something that occurs all the time. I mean, it's when you have really a turbulent cascade that you get this kind of heating. So interestingly now, if you plot the distance to the mirror threshold, which is obtained here by this formula. I mean, this is just the mirror threshold taking into account electron temperature, obtained by in the paper by Côte actually. And you plot it as a function of time. You find that 0 is the threshold for very long wavelengths. So since we are in a small box, there will be an effect due to finite wavelengths. And you find that you go to the mirror threshold and stay there for all the time. So you are already bounded by the mirror instability. If you look at the fluctuations in magnetic field, so at the beginning you drive Alfvén wave turbulence, but then the fluctuations of perpendicular magnetic field start to decrease and then go to a rather small value. I will explain these peaks later on. And associated to it, the drive of the parallel velocity, the velocity parallel to the direction of propagation, increases and then saturates again. So there is a growth of nonlinearity, and in the end, you cannot say you are anymore in a regime of Alfvén wave turbulence. You are dominated by mirrors. And at the beginning, the first phase of very strong growth of temperature here can be associated with the existence of Whistler modes that you find here superposed on the parallel velocity component here to the large scale fluctuations. And again, a spectrum which shows this clear break at the ion zero scale due to the fact that you really have two scales here, the scale of the Whistlers and the large scales, and this influences the spectrum in an obvious way. So if you change now the forcing, instead of taking a forcing at small scale, you force at large scale, of course then the time scales are different, but the phenomena is the same. So the structures, the mirror structures that are obtained are this form. I mean, depending on whether you force at large scale or you force at small scale, you clearly see that you have very small regions of BZ here. This is the magnetic field component perturbation along the ambient field, and these magnetic holes are already existing in the turbulent environment, and superposed in red here is the electron velocity. And inside these magnetic holes, I obtained very intermittent effects associated probably with a resonance phenomena, like an Alfvén or Whistler resonance. So these phenomena are extremely singular, and that's what necessitates actually the use of dissipation in the simulation. and actually have a strong effect also on the temperatures. So you have mirror modes embedded in Alfvénic turbulence, and another interesting effect is associated with the spikes you were seeing on the magnetic field Vy for long times, and which you actually can identify on the parallel heat flux of the electrons. So I average the heat flux over the side of the domain and show it as a function of time, and I have this very intermittent event. And these are associated with the growth of quasi-monochromatic modes, which I have identified possibly as slow waves. And these slow waves should be damped, and they are damped because they grow and then do not stay for very long. They grow from nonlinear interaction, and we still are working on this identification. What are these phenomena? These phenomena occur at long times for large beta, and lead to the phenomenon of isotropization of electron temperatures. You see that these events here associated on the electron temperature, and then the equalization between parallel and perpendicular electron temperature are already associated and linked with the occurrence of these slow waves. So this is just to show that in a larger domain, this kind of slow waves appear, but at the same physical scale, so it's not a numerical effect. And finally, to mention the importance of electron dynamics, I will show that if you assume that the electrons are isothermal, which might look like a reasonable approximation, then the behavior is very different. Instead of bumping onto the mirror instability and staying there close to the mirror instability, what happens is that the perpendicular temperature grows, the parallel temperature also grows, but then grows very strongly and crosses the perpendicular temperature, leading to a loss of, there is no mirror instability anymore. And what you find is that the spectrum is much shallower. Solitary wave structures appear, even though the amplitude of the fluctuation in the parallel direction are quite small. But the dynamics is very different, and the main difference is that you don't have Landau damping of the electrons. So even though you are not at the electron scale, you are mostly at ion scales, the isothermal approximation cannot be imposed and do not give the same results at all. So as a summary, I want to mention that the important thing here is that temperature and isotropy are generated. Perpendicular ion temperature become larger than parallel ion temperature. Electron temperature undergoes smaller growth, but with parallel temperature which dominates. The growth of anisotropy is clearly limited by the mirror instability. There is a growth of large amplitude quasi-monochromatic slow modes which lead to equalization of parallel and perpendicular electron temperatures. The mirror mode coexists with Whistlers and cows, and but the interaction between these waves and the mirror inhomogeneities lead to very intermittent resonant effects, which actually can then propagate Whistler waves away from the hole. And in the fully developed mirror turbulence regime, kinetic Alfvén waves become really subdominant compared to the beginning of the run. So meaning we are already in a regime which has nothing to do with the dispersive Alfvén-wave cascade that we were talking about before. And maybe there is truly a mirror turbulence. Okay, so thank you very much.
Okay, more questions?
So an important issue in my mind is how does the mirror mode saturate? And in these simulations, you're showing the formation of holes that in principle could conserve mu. You could have a saturation of the mirror mode and all the time conserve mu. There are other models of the mirror mode and the fire hose in which you assume that they cause real pitch angle scattering, that break mu invariance and scatter. Mm-hmm. And if scattering occurs, then that's an irreversible process that's giving true heating of the particles. This is work that Pratik Sharma and L.A. Quadrat and I did, where we impose scattering whenever you exceeded the threshold for an event. But if instead it forms these little holes that conserve mu and the particles just, you still reduce T perp because the particles collect in regions of low B, then that's a reversible process and there's no net heating of the particle.
Yes, I agree with that, yes. All the heating I was showing here is reversible.
All of the,
It's reversible, yes, definitely. But well, we have also included some collisions. I mean, the runs I've done here is without collisions at all. But the only way to actually get irreversible heating would be to actually put some amount of collisions or scattering, but we don't have scattering here.
so
It's very interesting that in our data, we can turn off collisions. Like the stuff we were showing is very low down in the collision waves. There are no collisions, and yet there's hot plasma and strong fluctuations at short time scales near these instabilities. So something isn't.
And how do we tell the difference between net heating and reversible heating in the solar wind wave?
whether mu is conserved or not.
How do we measure that?
You'd have to know mu at 2 different locations.
Sorry?
You'd have to know mu where you measure it now and where it had been earlier.
Yeah, well, that's kind of hard, is it?
It's not too hard. You can get synchrotron radiation near the sun, and you know the B field. That should help you, right? And then you can measure your spacecraft right here.
No, but Greg wants to know whether mu is conserved sort of right there at the mirror threshold as opposed to overall in the bulk.
Well, we could look, I mean, we were just saying.
We can just plot T perp over B across that entire plane and see if it's constant everywhere and the plasma is hotter, then I'll be very confused. But if it changes along the instability threshold, that would tell us something. I'm not saying it would be conclusive, but it would tell us.
Can you not just track, particularly if you've got your little kind of beam surfing in front, can you not just track them through mirror modes and looking, one side of the mirror mode and the other side of the mirror, just see what they do as they go through it?
The heating happens like that.
Well, also,
Well, but in these equations, at this scale, there should be no reason why you should conserve mu. I mean, you have all kind. I mean, it's
also
far from.
this mu conservation is I mean, if you make a delta B over B that's not too small, then you might be, what you're conserving is the exact mu, right? So as you're making a magnetic field line wiggle, you're changing the definition of V perp.
And also
Right?
remember, they have
it's
quite
a
sharp
question.
edges.
So when you're trying to track conservation, you're looking at V perp with respect to the exact local magnetic field.
Yeah, remember that whatever scale they have as well, they often have quite sharp edges and then kind of flatter bottoms over. So you can have quite sharp boundaries, or quite sharp field gradients within them, even if you're
That's a very
quite
large K-parallel situation.
Yeah, yeah.
Yeah, so if those gradients are strong enough, then you would break mu conservation.
Yeah.
That's right.
Another possibility is going to higher dimension. I know it's computationally hard, but
That's what we are doing right now. But
you do your 3D simulations more
yes,
easily
yes,
break.
definitely.
But there's evidence of holes in the solar wind.
Yes.
Yeah.
Oh, yeah.
Yeah.
I mean, I'd like to hopefully regroup in a year or so and really get into this, because I think at the heart of this is to the extent that a gyrokinetic or gyrotropic treatment of this is sufficient when you talk about is mu conserved or not.
But not gyrokinetic. Because if you think particle
cannot.
trapping in fluctuations is important, you cannot do trapping.
Yeah, well, exactly. I mean, isn't that kind of one of the points of this? How far can we push these treatments?
Well, but he's trying to go beyond gyrokinetic.
Mhm.
But definitely, in most of the runs we've done, trapping doesn't seem to be the main effect, except in a few simulations that we've performed where we clearly see signs of trapping. In the runs I've shown there before for the saturation of mirror instability, trapping does not play a role in saturation. And so, I mean, I'm not convinced that you really should always take it that.
But if the particles are not trapped, how are holes going to saturate the pressure? Because there's if you make a delta B parallel over B, right, and if you average this over particle trajectories, this is going to give you a non-zero contribution to impressions of the only from
You were showing that there's a density rise in the holes. Right?
That's
there are particles trapped there.
Yeah.
Well, Okay.
Well,
longer
it's
there. They
more,
don't have
it's
to be
more a
trapped.
temperature increase than a density increase, just empirically.
Is it?
Yeah, we've
What's
looked
the
at,
pressure is.
yeah, there's a statistical, you look at 10,000 holes, it's like 70% goes into temperature and 30% into density or something like that. A big question is
But it's
why those
perpendicular. It's
ratio.
perpendicular temperatures, then, so they are trapped.
I can say that there is in the model we've performed where we couple the large-scale asymptotic expansion for mirror modes to the quasi-linear diffusion theory. We have nonlinear anode damping that actually can saturate the growth of mirror modes. So
By
that's
holes.
mirrors.
No, in saturated structures are holes.
In that case, no. In that case, hams.
Right. So when we're talking about holes in the solar wind, is there any way in which things can saturate by holes, but not by trapping? Humps, I totally agree.
Yeah. Well, I mean, it's.
Well, maybe just want to think about it. I'm conscious that our photographer is here,
Okay.
waiting. So thank you very much again.
Thank you.
Thank you. Thanks all. So let's go and get our photograph.